AP Calculus AB, Unit 9, Day 3 lesson. So this is going to be the fundamental theorem of life or calculus or whatever. So we've talked about the fundamental theorem of calculus before, and it says the derivative of big F is little f. So this is essentially the same thing as f prime of x, right? If you integrate a derivative, you get the original function, you plug limits in. That seems like a pretty basic idea. And another way we could write it, we often use little f for all our functions. So say you have little f prime, you're going to get little f as the antiderivative, and then you're going to plug the top limit in first, and then you're going to plug in the bottom limit in second. So that's fundamental theorem of calculus, part 1. So just going to this, big F is actually the integral of little f. Because if you take the derivative of this, you get f prime equals little f, which equals the area under the function, right? You get the antiderivative. Little f is, the actual original function, the y values. As far as like motion, it's the position. F prime is the slope of the f function, which in terms of motion is velocity. And f double prime is the concavity of f. In terms of motion, that's the acceleration. And just for fun, the third derivative actually has a special name, more specifically related to motion. The third derivative is called the jerk. And you can imagine like jerking something, you get that extra change in acceleration. It's a derivative of acceleration. So anyways, anytime I want to, let some of my feelings out without being too obvious, I could be like, you're being such a third derivative. Just kidding. Whatever. All right. So let's kind of maybe relate this idea to sort of like more real life situation. Like, what do you weigh now? We could go with like, let's say you weigh 140 pounds. And what did you weigh when you were born? Say 6 pounds. Okay. Now, the difference between these is actually the accumulation of all the changes in your weight. So if we take the difference in these, we get 134. This is the difference in all the changes in your weight. Sometimes you gained weight, sometimes you lost weight. In the end, this is the overall change. Now, these changes, thinking in terms of more calculus, it's the rate of change. It's the derivative. So you could think of this as the accumulation of all the changes, which is really just keeping track of the derivative. So another way to kind of represent this is to say, okay, let's accumulate, right? So that's what integrals do. They're accumulators. So it's the accumulation of all the derivative. And if you do that, you're going to get the change in the original function. Now, what we could do is we could kind of, and this, by the way, looks exactly like the fundamental theorem of calculus part 1, right? We could move some things around, like move f of a over to the other side, just algebraically. And now f of b equals f of a plus the integral of f prime from a to b. And the way you could think of this is your weight now, 140 pounds, is your weight before when you were born, plus the accumulation of all the changes in your weight, right? That's what each of these terms would be. So you can think of this as you are today, right? You are today what you were yesterday or before, plus the accumulation of all the changes between yesterday and today, which would be this integral of the derivative. So whatever the status is now, it is what it was before plus the changes that have happened since then, right? Another way you could say it is you are now what you were before plus all the changes between before and now. All right. So this is a good way to think of it because we're going to be using this idea and applying it to, some more like kind of real life scenarios, and this will help even on the non real life scenarios. It kind of helps. Now on a graphing calculator, this is something we could really take advantage of on some problems. So if I give you an initial condition and then I give you the derivative and I want you to find the value of the function at some other time, so far what we've done is we integrate the derivative, get a plus c, use this to find plus c, then we have a function and then we plug 5 in it. But there's one little hiccup here. This is right here. This is something you can't integrate. You can't integrate that. I don't care whatever tricks you try, you can't integrate it yet. In BC, this is actually one I'll show you how to do. It's called integration by parts. But even if you could and you had a graphing calculator, it's just not worth the effort. And I guarantee even in BC, you're going to run into derivatives that you can't integrate. So what we want to do is we want to take advantage of this idea up here. Okay. Fundamental theorem of calculus part 1. We know that the original, this is what we would usually do. We'd say, this is what we would usually try. We'd say, okay, let's integrate the derivative, right? So let's integrate x to the third e to the x dx. And you'd be like, well, could I try u substitution? No, nothing works. You're stuck. Okay, but your calculator can do definite integrals of anything. It doesn't use the derivative rules. So what we want to start off with is like, okay, well, if I have the derivative, let's use that. And if I integrate the derivative, I'm going to get the original function. I want 5 and I have 2. So let's put 2 down here and 5 right here. So you want to involve the one that you know and the one you're looking for. And usually you want to do smallest to biggest. It's the least confusing. So now if you integrate f prime, you get f, and then you plug the top limit at first, and then you plug in the bottom limit in second. Okay? We're going to use this to help us find f5 because our calculator can do this. We know this. We were given that, right? So then we can move f5. We could add f2 to the other side and kind of move things around, switch sides. So f5 equals f2 plus the integral from 2 to 5 of f prime x dx. I just start with just really basic kind of idea of fundamental theorem of calculus part 1, which is, I think, kind of like a basic thing. I don't memorize it. It's just like it makes sense. If I integrate derivative, I get the original function, right? And I plug top limit first, bottom limit second, because that's what I always do. Now, on our calculator, we have f2 is 12. And we want to integrate x cubed e to the x dx. I put a du there. Okay. Now, our calculator can do this. Just to remind you, I wouldn't do it on the graph screen, but we do need our calculator. I would do math 9, which gives you f and int. And on my calculator, because mine's older, you would type this in x caret 3 times e caret x. You might have parentheses depending on which way you select it. Comma x, comma 2, comma 5. With respect to, this is the dx, this is the lower limit, and this is the upper limit. So Batteries are low apparently. So I'm going to do math 9 x to the third times e to the x, comma 2, comma 5. And there we go. It is 10,967.79566. I'm just going to write a couple extra decimals just in case I need to use this for another answer, another step of work. I'm going to want to carry more than 3 decimals at that point. Now here I can just say plus 12. And by the way, I could have done all of that just in one line of calculations, but we get 795. If you truncate, which I always like to do, but if you don't want to truncate, it'd be 10,979.796. You could round. But even if you could have done this one by hand, this is way faster, and way less mistakes. Okay? Now we can, this idea now, you can say, well, the function at 5 is the function at 2 plus all the changes in the function from 2 to 5. It's kind of like the fundamental theorem of life thing. By the way, don't write fundamental theorem of life ever, because that is technically not, like, that's just a kind of interesting way of connecting it to life that Mr. Statham used to talk about. So don't write it on your AP test because they won't know what you're talking about. It's fundamental theorem of calculus. So, yeah. Anyway, so, the function at 5 is the function before at 2 plus the changes in the function from 2 to 5. Should kind of make sense, right? Just with this idea here. Now, we can also go backwards. We could say, well, I know the future value and I want to know previous value. Well, the same thing. And just to not make it complicated, I would always just start with this. Okay, I know the derivative. If I integrate it, I get f. I want to, and I know 5. I'm always going to put the small one at the bottom, the big one at the top. So that's going to give me f5 minus f2. I don't feel like I need to memorize this. And I use this, I just start with this every time. This is what we want this time, right? So if we add it to the other side and subtract this, right? I mean, I don't usually show this work, but this is what I'm doing. And I'm subtracting all this stuff. Okay, so then we get f2 equals f5 minus the integral 2 to 5 of x cubed, or I guess I could just put f prime of x still if you want. You can start writing numbers in. So the function before is what it is later. Take back all the changes that happened to roll it back to what its previous value was. So f5 is 12, and then we're going to integrate x cubed e to the x dx, and even if we could do it by hand, it would just take a lot longer. Now, this happens to actually be the same value we got before, but here, let me show you how we can do this all in one line. We can say 12 minus math 9 x to the third times e to the x. So we could just do this all in one line. And just write the answer. So the answer is f of 2 equals negative 10,955.795, truncating, 3 decimal accuracy, rounded or truncated. Anyway, so, or, if you did round it, you get a slightly different answer. But this is going to be really handy. It's going to help us do problems we couldn't do without a calculator. It's going to help us do problems that we could do with the calculator. All right. Are you guys ready for it? The return of the fundamental theorem of calculus, part 2, the revenge of the fundamental theorem of calculus. Anyways, there's a part 2. We've been talking about part 1. And part 2 is the same exact idea, but the other way around. So fundamental theorem of mechanics part 1 says if you integrate a derivative, it undoes it and you get the original function. This one says if you take the derivative of an integral, they undo each other and you get the original function, right? These cancel each other out essentially, just like the other way. So, idea is intervals, so it should be integrals and derivatives canceling each other out. That's kind of the basic idea. But what if there were some limits? Because usually we're doing part 1 when there is limits. So what do we do? What do we do with the limits? Is it just fx? So let me, show you. All right, let's see. I don't know. Why don't you guys decide which one you think it is? Here's a specific example. Multiple choice. By the way, none of you guys can integrate that. You can't integrate this. Okay, just letting you know. And it's like the derivative is going to do the integral. But then what do we do with these limits? Do we plug them in? Top first, bottom second? Seems like a good idea. Possibly. A lot of these have that. Anyways, I'll let you choose. Choose one. I'm thinking, well, I don't know. I'll show you. Okay, so we have this. I'm going to kind of take a long approach to this, and then I'm going to show you a really fast way of doing it. But I want you to really understand it first. Okay, so what some people might think is they might think, oh, well, it's going to be sine, and then you're going to plug x cubed in and square it, and then it's going to be sine, and you're going to plug x in, and you're going to square it. And so you're going to get sine x to the 6th minus sine x squared. Is that it? I think that was one of the answers up there. That was answer A, but that is not correct. Okay. So let's take a break for a second and let's say, okay, well, let's treat this as like the derivative. F prime equals, F prime of t equals sine t squared. So I'm going to pretend that this is the derivative of a function first. And I'm going to rewrite it. So I'm going to say, okay, this is going to be f prime now. Now, the reason they have t's on the inside and x's on the outside is because otherwise it's going to get confusing. Like these are essentially kind of like t values, but if they're x values, it'd be weird to say that x equals x cubed. Using what we know, though, we know that integrals undo derivatives. So you get the original function, right? That's fundamental theorem of calculus part 1. And then we would usually plug the top limit in first and the bottom limit in second, right? Now, if we're going to go ahead and take the derivative of this, we can take the derivative of each term separately. Now, this involves the chain rule. The derivative of f of x cubed, this is an inner function. So it's a chain rule. You got to take the derivative of the outside first, leave the inside the same. But then you got to multiply by the derivative of what's inside. Chain rule. Minus this one right here, you got to take the derivative of the outer function first, and then take the derivative of what's inside, which is this time is just 1. So that's kind of the big idea here. If we were to rewrite this now, we'd have a 3x squared in front, and then we'd plug an x cubed into the sine function for t. See, if this said x and you're plugging x cubed in for x, that's kind of weird. Minus, there's a 1, and you're gonna plug just x into it. And then so your final answer is going to be 3x squared sine x to the 6th minus sine x squared. That is the answer. So if we go back up here, that was answer C. Now, I don't want to do all this work every time. The big idea is that when the derivative undoes an integral, yeah, sure, you just get what's inside. You get that function, and you plug the top and bottom limits in. But the one thing that you haven't done yet is you haven't finished taking the derivative of the inside, which is the limits. So here's the fast way of doing this. These are super fast problems, okay? So we'll do this problem again, super fast. I was just trying to make sure you understood why it ends up the way it ends up. So these essentially undo each other. And you plug the top limit first, so you're going to get sine x cubed squared, but you got to multiply by the derivative. And I'm going to just put it out front. I mean, a lot of times you do chain rule in the back, but I know I want it out front in the end, so I'm just going to do that. And then you plug the bottom limit in, x squared. But here's the thing you got to watch out for. You're not going to put 2x here. You're going to put a 1. It's the derivative only of what you plugged in. Okay, it's not, this would be x to 6. It's not 6x to the 5th. No. It's not 2x. No. It's just the derivative of what got plugged in. Just the limits. Okay? And so then your final answer is very quickly like that. These are fast problems. Okay? Now, so just to kind of summarize it, this isn't something to memorize. It's more of like steps to take. And usually put t's in here because it's a little weird if you have x's on the inside too. And then these are x and these are x's. So we get the original function and you plug the limit in, but then you got to multiply by the derivative of the limit. It's chain rule, right? Chain rule. Minus, plug the bottom one in, and you multiply by the derivative of it. Chain rule. So that's it. I mean, they're fast. Now, just as a little bonus problem, what do you think the derivative of this, what should that be? I mean, we could do the work. We say, okay, sine, plug 6 in, minus sine, plug 3 in, but then you got to multiply by the derivative. What's the derivative of 6? 0. What's the derivative of 3? 0. The whole thing gives you 0. Does that make sense? It should. Okay, because check this out. This right here gives you a number because it's a definite integral with actual numbers limit. This should equal some number, right? And then you're going to take the derivative of a number, right? You take the derivative of any number, you're always going to get 0 because it's not changing. So if any of your limits are just numbers, that term is going to go away. If they're both numbers, the whole thing's going to go away, which is probably very uncommon. So today's assignment is a worksheet. I guess, we could take a quick, So it's a worksheet, and these are super fast problems. So for instance, we could do, this is worksheet 9.3. Got a couple review problems right up there. And then we got some of these fundamental thermodynamics part 2, but these should be super fast. You should be like, okay, it's going to be cosine of 6 minus cosine of x. And then I got to multiply by the derivative of what got plugged in, which is 0, which is 1. That goes away. The answer is negative cosine x. Done. These are very fast problems. Okay? All right. You guys try the assignment?